Hi everyone, my name is Alex. I'm an engineer and my passion is design, development and prototype production of all sorts of engineering solutions. This episode is part 1 of a 2-part series on the reconditioning of my beloved Walter UTA dividing heads indirect indexing mechanism, or as you all know, in other words, it's worm drive. You see, I bought this dividing head some years ago from an old machinist veteran in used condition, and quite immediately then I re-scraped its base to decrease the swiveling error it had. This was not a wear issue. I assume this error was within tolerance at the manufacturer back in the day, and it was not large though. And after this I was very happy with it for many years. Just hit the pause button here if you want to know how I tested that swiveling error. However, over the years I've noticed that the backlash on this unit is not constant, quite regardless of how tightly you engage the worm drive. This eventually convinced me to test the indexing accuracy, of which I've posted a video some weeks ago. In said video, however, I only show the accuracy of the direct indexer, which is this disc and pin combination up here, which works like so. And the accuracy of this one is really fine on this unit, the largest error being roughly an arc minute. The same test, however, also showed me that the indirect indexer, which is this worm drive, did divide inconsistently and unprecisely. The largest error on the indirect indexer was roughly 4 arc minutes. Now, I didn't want to tell you about this problem in the testing video, because the problem is only half the story and the solution is more interesting. And here it is, at least part 1. The cause of the large indirect indexing error in this unit is corrosion on the worm screw. Now, I assume the former owner did not tend the oil filling in the housing very well, with the full screw up here and the side glass back there. And he must have been using flood coolant, a few drops of which must have entered the housing back at the shoulder and must have wetted or wicked the engaged worm screw. But I also assume that the unit was left that way for a quite long time, otherwise the corrosion would not be so localized and not be so deep. This way the worm screw, the hardened worm screw, essentially became an abrasive screw, which did wear away quite some material on the worm wheel. Machinist children, look away now. I know, that's nasty, and I should have seen this earlier. However, let's be honest, who disassembles equipment without obvious problems just for the fun of it? With this old file here, you can even hear it. It doesn't bite, so this worm is really hard. Now, beware, I'm not a professional gear grinder, but since this is non-customer work and not time critical, let's see how far we can push my workshop equipment without spending a lot of money on this reconditioning. I figure this is the best way to expand real-life skills and should also make for an interesting video. But that's for you to decide anyway. So let's take a look. I want to use this combined CBN and diamond cup wheel for this grinding job, and I want to use the face of it. And in order, let's say for example we want to regrind this lead screw, in order to cover the whole flank surface, our grinding setup must be able to tilt with the flank angle, and it must also be able to pitch a certain angle that depends upon the thread pitch angle. It is not actually the thread pitch angle, it's a compound angle, but it depends upon the thread pitch angle. So the setup must be able to tilt 2 ways, and let's see how we can do that. In my EMCO V13 lathes accessory list, there is also shown a support grinding machine which was available, and you can still find them around in a used condition, but people expect of up to €1,000 for it. And I wouldn't spend that kind of money for such a grinding machine, because for our problem at hand, we must be able to pitch the machine or pitch the grinding wheel with the thread pitch angle, and that's not possible with such a setup. So that's nice and neat, but no use for our purpose. We must stick to a custom engineered solution for a grinder setup. So, my old friend the Deckel D-bit grinder, I must borrow some parts from you. Yeah, you may say, why not instead buy a cheap grinding spindle or use some pneumatic grinder or a Dremel tool? This would spare the time to disassemble the D-bit grinder. Well, the D-bit grinder spindle is really good and rigid. It is very much of appropriate size for the job at hand. I have fitting wheels and wheel mounts for it. And even the motor is very suitable for the job at hand. And, believe it or not, stripping the motor and spindle off of that machine requires less than 2 minutes. I checked. And this includes taking off the wheel. But how to mount this in the lathe? Here is what I came up with. First, a standard boring bar holder. Then we need this swivel plate here, which is the backbone of this grinding setup. I made it out of some 10mm scrap plate, band on to rough size and machined on the round table. This is plunging down most of the material of the slots, because they are fairly deep. Then countersinking more slots, drilling, and very importantly, chamfering the slots on the machine, because manually this would give me quite some headache. Countersinking and chamfering the backside, that's it. By the way, the facets on the plate's face are not chatter marks, they are facets from manual interpolation with the DRO. This simplified machining a lot. Next we need the actual spindle holder. It is also made from that 10mm scrap plate material, quite simple. I didn't even take pictures of machining it. It mounts with 4 bolts to the swivel plate to allow for a wide range of pitching angles. In case you wonder why it is not surface treated and the other parts are, well, I had to modify this holder twice. The first versions didn't work well in terms of surface finish. This was caused by almost unfeelable vibration of the spindle, which I could remedy with this new holder, and it will go out with the next surface treatment lot. Anyway. Next is the spindle. It is clamped like so. And these clamps, they work so well that one must make sure not to over tighten it, because this increases bearing preload. Then we need this strut which holds the motor. It is held by 1 bolt and allows for a 2-way drive belt adjustment, so the motor can be positioned in various ways. And setting the belt tension. Of course we need the wheel. And this is how it swivels. Note that it swivels around the wheel's contact point with the work, which ensures that the contact point height is fixed. This is the disassembled dividing head. The housing and the guts of it. Here the eccentric sleeve with the bed worm screw. So how about the pitch of it? Well, Worm drives frequently have modulus pitches. This one is no exception. According to my measurement, it has modulus 1.5. This means its pitch is 1.5 millimeters times pi. Do I have that pitch on my lathe? Yes, there it is. But wait, neither do I have the 63 tooth wheel nor the 95 or 61. That was clear. What I have is these 10 standard gears and these 3 custom-made ones for cutting NPT thread pitches. Let's keep in mind this 63 to 127 and 95 to 60 ratio and the ZH shifter position. So with that factory setup, the bed slide moves by 63 divided by 127 times 95 divided by 60 times 1, which is the gearbox ratio with shifter position ZH, times the lead screw pitch, which is 6 mm in my case, and this equals 4.7126 millimeters per spindle revolution, of course. Comparing this with the exact pitch, 1.5 times pi equals 4.7124 millimeters. So obviously the factory ratio is an approximation, which is pretty unavoidable because of that nasty number pi. But the difference is only 0.2 microns per thread revolution. With 3 or 4 leads in contact in that worm drive, that difference is really insignificant. Believe it or not, I found the following ratio with the wheels which I already have. 76 divided by 127 times 90 divided by 80 times 7 to 6, which is the gearbox ratio with shifter position KC, times 6 mm lead screw pitch, and this equals, believe it or not, it equals the exact same number as the factory pitch. So I don't have to make or find more gears. Woohoo! The method I used to come up with this ratio here is called continued fractions. In case you need it, I'm sure you can look it up in a good machinist handbook or on the internet. So let's see. That's these 3 and this one. It's a close call at the collet draw tube here, but still works. So before we start grinding, let's put that pitch setting to the test. Here the indicator is riding on the bed slide, which is moved by the lead screw. That's a 10 micron per division indicator, so ignoring the corrosion wiggle, the screw seems to have an axial runout of about 20 microns. Let's see the other flank. About the same here. It's interesting that the factory screw grind seems to have 20 microns axial runout. I'm pretty sure about that because the shaft runout in my collet is quite good. That's maybe 5 microns here. And definitely below 10 microns on the far end. Before I started grinding, I also checked my tailstock, but you see that's fine. Also I checked the height. I hope you believe me, since the needle is not visible in this shot here. We must set the grinding spindle axis to half the included flank angle. Here that's 15 degrees. I set that by the tangents method. So zeroing the bed slide DRO here, then traversing for a fixed 10 millimeters or any other number you like. Now the bed slide position should read 10 divided by tangents 15 degrees, and that's good. As discussed before, we must also pitch the grinding axis. But how much? Well, it is a compound angle, and since I don't want to bore you to death, I just want to give you the formula here. So the optimum spindle pitch angle equals Arcus tangents of thread pitch divided by flank diameter times pi times the cosine of the flank angle divided by 2. And in our case, this gives 4.65 degrees. Now, this setting ensures that our wheel to work contact patch is as short and as much on center height as possible. It may look like so, for example. This in turn ensures that the projected flank that we grind is as straight as possible. I simply set this angle of the spindle holder on the swivel plate with the clinometer, but you can also use a sine bar or protractor to do that. So, ready for the first pass? I would be quite angry with myself if I messed up that unobtainium worm screw. So my pulse was 50,000. But everything seems to work fine. Look at that ugly corrosion. You may be wondering that my lathe spindle can turn so slowly. Well, it can't. What I'm doing in the background here has to do with that. You see, that's the full setup. To turn the lathe spindle so slowly, I drive it through an intermediate shaft with my welding positioner. Back to improvising again, huh? The speed is adjusted with a linear power supply. And for complete grace, I used this piece of flat iron as a torque strut. It works nicely. However, I cannot reverse the spindle this way because of the torque strut, wires and the coupling nut unscrewing. So I traverse back by hand. Then feeding. Coupling the drive again. Setting the torque strut. And off we go. I'm feeding short of 10 microns per pass, so this regrind required roughly 40 or 50 passes on both flank surfaces. This is my phone's perspective on this job. This is a final pass on that flank surface. And lo and behold, that worm screw corrosion has vanished from the face of the earth. I can only speak for myself, of course, but seeing it disappear soothes the soul of even the savage beast. Leave a comment if you think otherwise. Then, inverting the worm screw, rinse and repeat on the other flank. Luckily, the cup wheel didn't wear measurably unflat during this regrind. Finally, chamfering the flank tips with an aluminum oxide wheel. I seriously hope you guys are wearing safety glasses now. And here's the result.
Legs are a little rumbly after all that time sitting there. Why don't you roll me inside? We'll get the nurse to take the catheter out of me. All I want to see is my lizard still. We don't need nurses for that. I know how to do it. But don't you have to?
Of course, this regrind caused the A to B ratio on the flank diameter to become larger than 1. But who cares about that? The worm is still way strong enough. The contact with the old and worn worm wheel, however, gained a lot of backlash this way, but we are going to make a new worm wheel anyway. But let's see about that in episode 2 of this series. As always, thank you very much for your interest in this video. I appreciate your time. All the best, guys, thank you, and hopefully see you next time.